Who uses Robot C?
Woo!
Who uses LabVIEW? So it's not a big deal. A lot of the things we'll be explaining we have done in Robot C, but can definitely still be done in LabVIEW. Alright? So let's continue speaking up.
So Robot C versus LabVIEW, we use Robot C, we find it to be a little bit better, or at least we did when we were choosing which one to do at the beginning. We find that Robot C, they're smaller programs, so you can hold more, you can have more function on the brick itself, and there's also a faster execution time, so that the programs run more quickly. This is old information, we're not sure how LabVIEW has changed, but it probably works. A lot of teams do use it, so either way probably is fine.
So just a really quick thing to make sure you guys do, something we do is versioning and a change log in our programs. So every time we go to change something major in our program, or make big edits, we version the program. So for example, you can see there's an example name of our program, 4251, 42 teleop, so 42 is a version number. Always keep the old versions of your working program, and then keep a change log in like a comment section of your program. So for example, for us, we have just a huge commented out section at the top of the program that's a change log that shows with each version what we edited and what we changed. And then make sure you test multiple times before the competition. Test repeatedly. We make sure everything works 5 times in a row.
Robot C exposes the timeout for the FCS via a global variable. That global variable is N no message counter limit, and it is set to 750 in joystickdriver.c. But it's a global, so you can change it in your own local code. At the request of first, it was set to 750. 750, depending on how fast your code is executing, will give you 5 to 7 seconds before your robot will realize that it's not getting any new joystick messages from the field control system. You've lost connectivity. We drop it down to 150, which probably gives us a second and a half, maybe a second. And so when we lose control of our robot, it only runs for 1 second instead of 5 before it sits there waiting to reconnect. Have you guys ever been driving your robot and have it decide to keep driving even though you were done? So this shortens how long that'll happen for. All you have to do is put that first line in your code. Now, we tuned to find 150 for us. When we made it lower than 150, we were seeing dropouts that weren't real dropouts. The robot started to drive stuttering because it would think it hadn't gotten a signal recently enough, and so it kept stopping. Oh, no, I've got signals. Oh, I'm stopping. 150 was where it worked for us. Yeah, everybody's robot's going to be different.
All right. Drive code, a really important part of your programming. We really encourage you to make your own. But why? Big thing is it's customizable to you as well as it's personalized to you and your drivers, this game, and you'll understand it better. If you coded your drive code, you might have some more bugs at first that you wouldn't have if you just use a built-in program, but you know the bugs and you know how the program works. So if you want to change a specific part for the driver or the game, you can do that. So one of the big things that we always change is how we set the motors based on the joysticks. So a really simple way to do this is you just take the joystick values, which go from negative 127 to 128, and just set the motor equal to that. The problem you run into is the motor only goes from 0 to 100, and to 0 from negative 100 to 100. So you lose anything where the joystick is past 100, it's the exact same to the motor. The motor just thinks it's max power. So the first thing you want to do is you want to transform it so that the joystick goes from a negative 127 to 128 to a negative 100 to 100. So you're using the full joystick range when you're setting the motors. Along with that, we use a parabola. So normally, when you just set the joystick equal to the motor value, it's linear. As one goes up, the other goes up. Really simple. You can see from the graph. On the other hand,
It's the red line on the graph. That would be a linear, well, the red line on the graph would be an unadjusted linear control. So let me point at that. Where's the flag? So if you had a linear motor control, is you bring your joystick down, you're going to hit 100 backwards. You bring it down further, you're still at 100 backwards. This is that 100 to 128 or up unreaded. So you end up with a motor curve that looks like that, following this down, and then it's at max speed for that much of your joystick.
so we adjust it so that the joystick goes from negative 100 to 100, and then we add a parabolic function. So basically what this means is we will take the joystick value and we'll square it. So let's say the joystick is at a quarter of the way up. What we then do is we take a quarter and we square it, making it an eighth. So if the joystick is a quarter of the... Not yet.
No, a quarter squared is an eighth.
Oh, that was bad. A quarter squared is a 16th. Don't listen to me, I'm silly. So, let's say your joystick is at a quarter of the way up, you square it, it's a 16th, which means you're actually sending the motors a 16th power. But then when you get to full power, is it actually full power? It is, because if you take 1, square 1, you still get 1. 1 out of 1.
So you convert your 100, negative 100 to positive 100 to a negative 1 to positive 1. And then you square the fraction. Treat it as a percentage. So a half squared is a quarter. So half throttle gives you a quarter speed. Quarter throttle squared gives you a 16th speed.
So you have much finer control at slower speeds and coarser control at higher speeds. So this is really quickly the math to do that. We can show you this later and help you guys with this later if you want to add this to your own code. But first you square the joystick value and then subtract 100, which is your transforming part. The other thing we do with our controllers is we add a dead zone. So in other words, if the value is below a certain point, then just ignore it. We found that on some of the joysticks, when they first get plugged in, they might be sending really low values, even though you think they're centered, which creates sort of a creep in your robot. The dead zone makes it so it just ignores values under a certain point. So you subtract 100 to create that dead zone, then you multiply it by 100 over 128 times 128, which is that squaring combined with we're converting into the percent. And that actually evaluated is a number passive. Rather than doing that math again and again, we just do multiply it by the n number, which gives you that value from 0 to 100. So then to make it so if you move your joystick backwards, the motor will actually get a negative power. We need to multiply the sign back into the value, because we squared it at the very top, making it always positive. And there's actually a function in Robot C for doing this. And then you return that number to the motors. So that's really simply how you do it. Some other cool bits of our programming, low gear and programmatic gear shifts. So these are literal like a gearbox gear shift, but instead what we do is we take that final power we're sending in the motor and say divide it in half, which gives us a finer control at a slower speed. So you only have half speed. You don't have twice as much torque like you would in an actual gear shift, but it does give the drivers a little more control.
You control those with your joystick. The driver could select, oh, I want to go at 50% speed, and then maybe there's a button that has the values on the joystick.
The other thing, we always use tank drive on our joysticks. But the problem we found with tank drive is if you're trying to go half speed directly straight, it's kind of hard to do. So we also add in an arcade drive on our top hat. So we have the combination of some of the finer control of the finer turning control of tank drive, and the ability to do straight and pivot turns on the top hat. Along with this, built-in PID logic. So Robot C has built-in PID, or proportional integral derivative logic. Basically what PID does is it allows you to send the motor a speed to run out instead of a power. So without PID, you're sending it a power to go at. If the motor gets slowed down because there's more load, it doesn't make a difference to the motor, you're just giving it a power. On the other hand, PID allows you to send the motor a speed. So in other words, I always want this motor to run at this speed. Well, the motor will then, I guess the program will try to compensate for, let's say there's more load. Let's say you have more weight on it. The program will try to give it more power so it stays at that speed. And this is built into Robot C. All you have to do is you plug in an encoder from the motor to the correct port on the motor controller, and then go up to your Robot C configurator and just say, check, I want PID logic. And that's it.
Okay, anti-stall logic. So this is again pretty simple but pretty valuable stuff. We only use it in autonomous. Autonomous, the robot's going to go try to do stuff and you don't have the opportunity of a driver to stop doing something that is going to cause your robot problems. With our anti-stall logic, anytime the motor power is not zero, when it's trying to do something, we store the encoder value, we wait, we read the encoder value. If the encoder value isn't changing enough, we take a 2-second timeout, let the motors cool down, try again. So this doesn't have any big ripple effects. You can implement it right down in your load. I think I mentioned to some of the people here, we have a routine that we reuse in our autonomous. It's move, distance, at speed, on heading. We call this with 3 variables. The distance you want to go, how fast you want to go, and what direction you want to go. And it just takes care of making that happen. Well, while it's making that happen, if it runs into something and those motor encoders bog down too much, right there in that buried bit of logic, it just says, let's take a timeout. So he sets the motor values to 0, he loops for 2 seconds, and then he lets it go again. And so in autonomous, you guys will see our robot get into a pushing match, stop, and then try again.
So here's an example of that. So this is an autonomous, and you can see we hit this robot, and our motor is stalled out, so we wait. It tries again, still stalled, and it stops again. And it basically is just a little loop where it'll try. If it still is too bogged down, it'll stop. It'll wait. Try again. We'll run that for just.
And so we never finished that autonomous run because it stayed down in that move distance at speed on heading. Move distance at speed, I guess. But we didn't burn out any motors either. We would try for a second or two, take a break. Try for a second or two, take a break. And it just kept doing that for the last 15 or 20 seconds of autonomous that time because we had run into a really big heavy robot. But we knew we would be good to go when teleop came on. So and if they moved, we would finish our run.
So it basically acted like a safety system, so you didn't fry your electronics.
You got it. Anybody here ever fry a motor in autonomous? Okay.
Those are the fingers. Yeah. So sporadic guide encoder values. We found that sometimes encoders will get messed up between writing to the I2C and reading them. And you get just a really weird encoder value that's way off from what it actually is. And it makes it so that, let's say you were moving until it's greater than this. It'll satisfy that condition, and it makes it so that you stop moving and you move on to your next point. The way we've dealt with this is another decently simple. It's basically if you take this encoder value, store this encoder value. If the next encoder value is too far off of this, is more than a certain number off of this, then just disregard it. Don't use it.
How we actually ended up implementing this, and Joey Diamond implemented this. That's why there's a little less familiarity in the team right now. It looks, so normally when you're moving a distance, you're looking for a threshold value, right? When the encoders get to this value, I've finished the move. And then when you hit that threshold, you exit that loop and you go do something else. Well, every once in a while, a bad encoder value comes through that satisfies the threshold. Happens maybe 1 in 1,000 times, maybe closer to 1 in 2,000 times, but somewhere in that range of an encoder reads, every 1,000 or so you'll get a bad one. Whenever we get a threshold value, we then store that value, watch for it to change, because you can sometimes read the encoder and for 3 to 5 subsequent reads it won't change yet. It doesn't update as fast as your program is looping. So you watch for the encoder value to change. When it changes, you read another encoder value. If it also satisfies your threshold, then you've had 2 readings in a row that satisfy your threshold. Go ahead and take the threshold activity. Stop that run, do your next turn, do whatever comes next in the program. If, on the other hand, after you've hit the first threshold value, the very next value is back below threshold, start over and look for your next threshold event. So where one threshold event, one bad threshold event would happen 1 in 1,000 to 2,000 times. If you're looking for 2 in a row, that's then going to happen 1 in 1,000,000 to 1 in 4,000,000 times. It's the odds of you having 2 bad values in a row are a whole lot less than you having 1 bad value. And so all we do is we look for a threshold value, and when we find it, we look for another one right after it. If we have 2 in a row, do the activity, but require 2 in a row before you move on.
Some other things that we do, multi-threaded programming. It makes it really easy to have multiple things happening at once, and some timing pieces can be similar, such as in the block party robot, we had the robot scoop and move forward at the same time. It's doing a couple things at once. It's sometimes going to be easier doing this, and it's easier to do automated routines like that. A couple of cons, you lose some CPU time as it's switching back and forth between threads, and the CPU chooses when to switch back and forth between threads by normal. So you can't say, well, wait until I'm finished doing it. It'll switch in the middle of like you doing an operation. So let's say I'm taking an average in this thread, and I'm reading the average in this thread. So here I'm saying I want this value plus this value plus this value plus this value divided by 4 equals this, and then from over here I say this, and I use this to do something else. Well, the problem is let's say I'm doing the calculation in this thread, and I've added this number, I've added this number, and then it switches the other thread and tries to read what the variable equals then. The problem you're going to run into is it's going to be astronomically larger than what you actually wanted because it hasn't divided it yet. You can fix this in Robot C by using their 2 commands, hog CPU and release CPU. Whenever you put a hog CPU in, it will force the CPU to stay on that thread until it sees a release CPU. You just have to be careful with them because you can bomb a program that way. So multi-threaded programming, we use it. We found it to be really good, but it's just kind of a personal preference. You can do a lot of the same things in a single thread program. Xander's third-party driver suite is now built into Robot C, but it's basically just a suite that allows you to access all of the different sensors that are provided by High-Technic, as well as Xander's written drivers for the prototype board, and a couple other things. But, yeah, Xander's third-party drivers.
Automated functions. So like someone mentioned before, they had a button that would pick up the bucket. I think we were done in the video earlier. And if you have an automated function like that, where you just press a button and it's going to go through this series of motions, it's very helpful because it can cut down on driver error and it also can increase your speed. Robots are really good at doing the same thing multiple times, and they can also handle doing more than one thing at once, where a driver would have to press each button individually. It's harder for a driver to figure out the exact angle that your arm needs to be when you're picking up blocks or when to clamp, but a robot can do it all in succession.
So a good example of this, I think we mentioned earlier, is our preset positions. This was ringing up 2 years ago, and we basically programmed the height positions to the robot, so all the driver had to do was press one button, and they would go to each one of the 3 heights.
This next video, it's an example of a more complicated automated function. Here you can see it's an arm with multiple joints. So if you press one button to aim it, you press another, you carry out that complex series of maneuvers correctly the same way every time. While a human, manipulating all those joints at once would take a long time. And it wouldn't be very accurate.
Those were all one-button presses that ran pretty complicated functions on the robot.
The other thing I'll say they do with this, as part of building it, is they will use a program called GOM Player, G-O-M Player. It's a nice little video player for your laptop, for your PC, but it supports slow motion and frame by frame. So like that motion you saw where it flicked the basket and made it roll, that was lots and lots of trial and error, programming 1, 2, 3, 4 joints to do that flick as a smooth, instead of a elbow out, then wrist out, then hand out, just a smooth motion. They videoed it in slow motion, watched frame by frame, and adjusted the timings of different positions of different joints on the arm to make something that looks that human. That wasn't just that was a couple days worth of work to get those kinds of motions fluid like that.